To understand Malus's law, we must first look at unpolarized light. In this state, light waves vibrate in multiple planes perpendicular to the direction of travel. When unpolarized light passes through a polarizing filter, only the components of the wave aligned with the filter's axis are allowed through, resulting in linearly polarized light. Malus's law specifically describes what happens when this polarized light hits a second filter, called an analyzer, which is oriented at an angle theta relative to the first. Because the intensity of light is proportional to the square of its amplitude, we must square our cosine term to find the transmitted intensity. This brings us to Malus's law. The transmitted intensity, I, equals the initial intensity times the square of the cosine of the angle between the polarizer axes. When the axes are parallel, the angle is 0. Since the cosine of 0 is 1, all the light passes through, resulting in maximum intensity. When the filters are crossed at 90 degrees, the cosine is 0. This results in total extinction, where no light passes through the second filter. If we plot the intensity against the angle, we see a smooth curve. Notice how the intensity drops to half at 45 degrees and hits 0 at 90. Let's solve a problem. If the analyzer is rotated to 60 degrees, the cosine is 0.5. Squaring that gives us 0.25, meaning only 25% of the light gets through. In summary, Malus's law allows us to precisely calculate the reduction in light intensity based on the relative orientation of two polarizing filters. This principle is used daily in polarized sunglasses to reduce glare and in photography to control reflections. Thank you for watching. Generated by Vision Solve AI.